Alright guys, so this video is going to be over gas laws. So hopefully this will be a basic review over something that you got maybe a couple years ago in chemistry. But what are we talking about with gas laws? We're really talking about relationships between pressure, volume, temperature, and if we can get to it, we'll talk about the amount of gas, that little n maybe seems familiar to you. It's the number of moles. Yeah, we're going to be talking about moles again, so that's going to be awesome. Alright, so let's start off with this container, and this container's got like a little plunger in it, so it seals it off. Okay, and that plunger can move up and down, so it's like a little piston that goes for the container. We got all these little gas molecules moving around in here. Okay, so if we talk about this little container as being a sealed container, everything that we're going to talk about then has a constant amount of gas. So we're not gaining gas, we're not losing gas, we're talking about what's changing on the inside. But here we're going to talk about, okay, let's keep the constant temperature of the gas. So we're not changing the temperature at all. Okay. Now let's just say that we decrease the volume of the container. So the volume goes down. Okay. The plunger goes down. So the volume goes down. Okay. Well, what's going to happen to the particles on the inside? Well, if we think about the fact that it's a constant temperature means that the kinetic energy of the molecules are going to stay the same. It's not going to go up or down. Okay, it's going to stay the same, which means that the speeds of the particles are not going to go up or down. Okay, they're going to hit the container walls with the same speed, which means they're going to hit with the same force. But we know pressure not only talks about the rate at which the molecules hit, but it also talks about the frequency at which they hit. And if the volume goes down, that means the molecules are going to hit more often. Even though the same amount, they're going to hit more often. So the pressure is going to eventually go up in this container. So and vice versa is true. If the volume goes up, then the surface area inside the container walls is going to be bigger. And since the temperature stays the same, the speed stays the same, then the pressure is going to go down. So we have something that's inversely related, something that says that pressure times volume equals a constant. Or another way of looking at it is that if you multiply pressure and volume in the initial state, then that has to equal the pressure times the volume in some final state. And this right here, you remember, is Boyle's law. Okay, so P1V1 equals P2V2. Alright, so that's constant temperature. So what if we take the exact same container, okay, same plunger, and we hold something else constant this time? Let's hold the volume constant. So we are holding the volume constant. That plunger is not going to move. Okay, same gas that's inside, all buzzing around. So let's say, since we're not holding temperature constant, let's increase the temperature of this. So what does that mean? That means the particles are going to be moving faster on average. Okay, that means they're going to hit with a greater force. So what is that going to do to the pressure? Well, if you have faster particles that are going to hit with more force, that means the pressure is going to go up. So and vice versa, if you have a temperature going down, then the pressure is going to go down because they're moving slower and they're going to hit with less force. So what we have here is pressure divided by temperature is equal to a constant. Okay, or it's in a direct relationship, while the other one was an inverse relationship. Another way that we could talk about this is P1 over T1 equals P2 over T2, or saying that the initial pressure and temperature divided by each other equals the pressure and temperature at some later time divided by each other. And this one, if you remember, is Gay-Lussac. So Gay-Lussac. That was his law. Alright, last one of the big three that we'll talk about is we've held we've held temperature constant, we've held volume constant, so now let's hold pressure constant. Okay, now the thing about holding pressure constant is we have to understand what exactly pressure is, so constant pressure. And the things that go into pressure are the speeds of the particles, which is closely related to their kinetic energy, which is obviously a measure of temperature. So temperature is speed, okay, basically, okay, or I'll put proportional to speed. Okay, and then we have the rate at which they hit, and the rate at which they hit is tied to their speed, but it's also tied to the surface area of the container itself, the surface area. If you have a large surface area versus a small surface area, then it doesn't matter what the speeds are, you can change the rate at which they hit. So let's talk about increasing the temperature of this thing then. Okay, we're increasing the temperature. So these particles are going to move around faster, 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 faster. Okay, but that's going to increase the speed, which will try to increase the rate at which they hit the container's size. But if we're holding pressure constant, that means we have to do something to the container in order to keep the rate the same. So that is going to be where the surface area comes in. If we increase the volume, then we can dictate how the rate's going to hit. Even if they hit harder, we can make them hit less often, and that'll keep the pressure constant. So we have temperature going up, volume is going to go up. Same thing here is that if volume goes down, that's going to decrease the surface area, which is going to try to increase the rate. So in order for us to keep the pressure constant, we have to decrease the temperature. We have to decrease the speed at which they're moving. Okay, so again, this looks like this. We have volume divided by temperature, because it's a direct relationship, is equal to a constant. Or we can look at it as V1 over T1 equals V2 over T2. So that's constant pressure. And this one was Charles' law. And those are the big three. Okay. Now, each one of these three laws, we were holding something constant. All of them were a sealed container where the gas could not leave or escape, or more gas come in. So why don't we change that up? Why don't we have our same container, same plunger, okay? But now we've got a little hole on the side of it. So we have some gas that can escape if we want to. Okay. Couldn't even tell if that was the word hole. So let's try that again. Hole. There we go. We got a hole on the side. Okay, so let's talk about if we not keep anything constant. Pressure. Well, let's actually scratch that. We're going to keep pressure and we're going to keep temperature constant. Okay, pressure and temperature constant. And if we do that, then we're not messing around with the speeds. We're not messing around with the rate at which the things are hitting, or the force, or same arguments that we have for pressure last time. So we're keeping P and T constant. Let's change the volume. Let's push the volume down. Let's decrease the volume. Well, if we decrease the volume on the inside, we're basically trying to increase the pressure on the inside, because we're decreasing the surface area that all these molecules are hitting, or atoms, or whatever we're talking about. All these gas particles are hitting. But you think about it, if you have like a syringe or even a balloon or something like that, and you blow on the balloon, you push on the balloon, and there's a hole somewhere, all the gas particles are going to come out of the hole. So if we're talking about the amount of gas in terms of the number of moles that we have, if the volume goes down, the number of moles that are actually in the container are going to go down as well. Another way of looking at it is that what if you increase the volume? Okay, this is like pulling back on the plunger of a syringe. You're going to decrease the pressure on the inside momentarily, which means that the higher pressure on the outside will push molecules in through the hole, and it's going to increase the amount of gases on the inside. So again, we have another direct relationship between the volume and the number of moles, or basically the amount of gas that we have. So volume over the number of moles equals a constant. Okay, whatever that constant is, I don't know, at least not yet. And we can look at it as being V1 over N1 equals V2 over N2. So some initial position of volume and amount equals some final position of volume and amount. All right, so if we put all this stuff together, what we're really looking at is that pressure times volume divided by the amount of gas times the temperature. That's just putting all the laws together. By the way, this thing is called Avogadro's law, and I'm sure you probably recognize that name, Avogadro's law. That's the name. And PV over N times T is equal to some constant. Okay, and you can look at it as being P1, wow, that's not a P, P1 V1 over N1 T1 equals P2 V2 over N2 times T2. Okay, that right there is called the combined gas law. Okay, it's got them all together. Okay, and if you ever needed to find something where things were held constant, let's say we hold the number of moles constant, which means it's the same on both sides and it cancels out. And what if we hold the temperature constant? It's the same on both sides, it cancels out. Well, then all you're left with is Boyle's law. Well, that's what we had when we held temperature constant. So P1 V1 equals P2 V2. So the combined gas law, this thing right here, is all the gas laws put together. Okay, but the question is, what is this constant that we have here? So we can find it experimentally by measuring the pressure, the volume, the number of moles in a gas, and the temperature of the gas, and just doing the calculation for that constant. And what I'm going to do is I'm going to put that into the questions at the end of the video. And so you're going to calculate the gas law constant. That goes right there. Okay. If you have any questions, put them in your video responses, or you can ask them in class.